Started. Lecture 7. So today we want to understand how to compute entropies in systems of free fermions. Entanglement entropies or entropy in systems of free fermions. And I want to start by reminding you what's special about systems of free fermions. So these are fine-tuned Hamiltonians. They are very special. And they have the property that we can efficiently diagonalize them. And we'll see that we can also efficiently extract entanglement entropies for large regions. So remember what the trick was. If we work with n qubits, then we have a local algebra of operators given by the Pauli matrices. And what we find in that case is that if you take the commutator, we saw that already, of 4 Pauli matrices, two Pauli matrices with 2 Pauli matrices, this gives you 3 Pauli matrices, okay? So if you now take the result and you commute with 2 Pauli matrices, you'll get 4, and then 5 and 6. And this keeps growing. And so what that means is that bilinears in Pauli matrices do not close a subalgebra with respect to this commutator. And that means that whenever you try to diagonalize a Hamiltonian that is expressed in terms of Pauli matrices, you'll have to really deal with the full algebra of operators or linear maps in our Hilbert space, and this is 2 to the n times 2 to the n. Okay? So there are no shortcuts with generic Hamiltonians expressed in terms of Pauli matrices. But it turns out that if we work with fermionic operators, which anti-commute, so the Pauli matrices have this strange property that when you are on the same side, they anti-commute, but when they are on different sides, they commute. So there is this mixed behavior. Okay. What you can actually do is you can work with fermionic operators which have these anti-commutation relations on-site and off-site. And then it turns out we saw that if you take the commutator of bilinear forms, quadratic term with a quadratic term, we saw that this is also a quadratic term. Okay? And so these guys close an algebra. And this algebra is only, it's whatever, you have n of such operators, so how many bilinear forms you can have, so order n squared, okay? And so we have a much smaller algebra there. So if we can stay within this subalgebra, we can efficiently diagonalize quadratic Hamiltonians. And the same happened with Majorana operators. We also argued the other day that if you look at commutators of 2 quadratic operators, the result is also a quadratic operator. Very good. So that's the reason why we like free fermion systems, because we can deal with them efficiently. How relevant they are to physics? Well, they are actually also relevant, right? But the main reason why we pay attention to them in this course is because we can compute with them. We can consider large systems. Very good. So let me focus first on a system with a Hamiltonian which is quadratic. So let's consider a fermionic Hamiltonian given by this expression. Okay? Where you can always choose A to be Hermitian, this matrix of coefficients here, you can choose it to be Hermitian. Then when I talk about such Hamiltonians, I'll be talking about particle number preserving Hamiltonians. Okay, so this is a fermionic Hamiltonian which has 2 properties. One is quadratic, And we like that because it implies that the cost is going to be some polynomial. So the cost is going to be just polynomial in n as opposed to exponential. But it will have another property, which is that it preserves particle number. It conserves particle number. What I mean by this is that if we define, so let's say, preserves particle number. What I mean by this is that if we define a particle number operator as given by again, a bilinear term, a sum of bilinear terms, then it turns out that you can check that this Hamiltonian commutes with the particle number operator, okay? So we'll be talking about this as a quadratic fermionic Hamiltonian which preserves particle number. And what does this mean? Well, it actually means that there is a symmetry, which is if you take these annihilation modes, AI, and you multiply each of them by the same phase, okay, which implies that AI dagger goes into conjugate phase, then you can check that this Hamiltonian is invariant, and so this phase is a U1 symmetry. In other words, whenever you see any term in this Hamiltonian such that it destroys a particle and it creates another one, so the total number of particles when the Hamiltonian does not change the number of particles. In particular, that means that the ground state has a well-defined particle number, and another property, the ground state of this Hamiltonian, will, if it's unique, if it's non-degenerate, it will have a well-defined particle number. And another property we will be using in order to describe the ground state of this Hamiltonian, it's Wick's theorem. Okay, which says that the ground state psi of H is Gaussian, is Gaussian, which actually means that it's completely characterized by knowledge of A dagger A, this expectation value, okay, and also A I A J. But in our case, since we have particle number preservation, if this is an expectation value on the ground state has well-defined particle number. If you kill two particles and you take the overlap with the ground state, which has two more particles than this state, then this is going to be 0. Okay? So we will not have to worry about this part by particle number preservation. So Wick's theorem tells us that all we need to know to completely characterize the ground state of this Hamiltonian is the expectation value of AI dagger AJ for I and J running from 1 to n. Okay? That will be a complete characterization of the ground state. So far we were seeing that, oh, great, instead of having to build a 2 to the n times 2 to the n matrix here, we can focus on an n times n matrix of coefficient. That's good for the Hamiltonian. But now we see that there is something analogous for the ground state. Okay? Instead of having to build a vector, so this ground state has 2 to the n components. Okay? It's a vector in a 2 to the n dimensional vector space. So to represent it, you saw that yesterday, you had to build, for a generic Hamiltonian, you have to build a vector of dimension 2 to the n. What we are saying is that in our case, the ground state of a quadratic Hamiltonian that preserves particle number, okay, that all we need is this, is n times n coefficients. There is a very important reduction in the complexity attached to describing this ground state. All we need to know is these expectation values, okay? N times n, different ones. Okay, so what's the plan then? what we would like to do today is to find the ground state of Hamiltonian like that, and then compute the entanglement entropy for different regions and see how that entanglement entropy scales. So what's our plan? Our plan for today is first, we're going to have to find these metrics, how much these expectation values are, okay, for evaluated on the ground state. For ground state of that Hamiltonian, which is quadratic and particle number preserving. Okay, that's the first thing we want to do. Then when we find the ground state, or the description, compressed description of the ground state, what we want to find after that is the same thing for just the reduced density metrics on a region A. Okay? So the story here is again the same, that instead of having to build this guy here, if this region A is of size L, this would be of L spins or L sides, then this is a 2 to the L times 2 to the L matrix. Okay? But Fick's theorem tells us again that all we need to worry about is something that will have size L times L. Okay? Questions?
Will the reduced density matrix still be Gaussian in a sense?
It will, and we'll see why actually. It's a good question. When you see why, you say, of course. But yeah, it's a legitimate question. Okay, so
does the complete description mean like we can actually write down the wave function in explicit form of wave function if we know all n coefficients?
it means if you spend enough time on computational resources, you could expand. You could get the 2 to the n coefficients of the wave function. They are all functions of these n times n coefficients. And remember what Fick's theorem says, right? I think I can write this here. So an example of what it says is that if you have, say, what is it? This one. AI, AJ, AK, daga, AL, daga. Okay, the expectation value for that state, which is Gaussian, is nothing but, and then you can expand it in terms of precisely the 2-point correlators, or the, yeah. So there is some expression. AK daga, AL daga, minus AL, some expression that I wrote just in case, but that only involves expectation values of quadratic terms. Okay? And actually, this is not so hard to prove. If you are interested, we can discuss this after the class. But I cannot discuss it now. So the idea is everything is contained once in let's see, this is, oh, okay. So yeah, in this matrix, n times n. Good, so our plan then was to find it for the ground state, then to understand how the reduced density matrix can also be expressed in terms of even smaller matrix of coefficients, okay, L times L. And finally, what we also need to do is to understand how to extract the entanglement entropy, or the entropy S of rho A, which is defined in terms of the reduced density matrix. We saw that yesterday. But what we're saying here is we are not going to build this rho A, right? This rho A is 2L times 2L. We're not going to build it, and yet we want to know how much the entropy is. And we'll see how we can still, just directly from this correlation matrix, we can extract this expression, okay? And finally, the other comment is that it is more convenient so it is convenient to work with a matrix M, which contains exactly the same information as the correlation, the 2-point correlators. Okay, so so giving this or giving that is the same. Okay, just more convenient to work with this particular linear combination. Okay, and I'm going to refer to this as the correlation matrix. Okay, so we know what the plan is, and now instead of find this or find that, I will just find analogously M, okay, for it. All right, so this should be simple. Let's see. So let's do point 1 of the plan. Let's find the correlation matrix for the ground state, and Big's theorem tells us that this is everything we need. So the first thing is I'm going to write the Hamiltonian that we had up there in this way, make it more compact, where I just build a vector with all the annihilation operators. Okay? So that expression is analogous to the one we had up there. Okay. And we need to remember that A is a Hermitian matrix, right? It's n times n, Hermitian. And so we know that we can always diagonalize it using some unitary transformation. So U is a unitary matrix n times n. Okay. This is diagonal, and it will look, and we've done this before, it will have the single particle energies in the diagonal. Okay. So now what we want to do is to choose a new set of fermionic operators given just by U daga A. Okay. So we had n annihilation operators here. We define a new set B by the linear combinations such that then H, well, that's a piece of cake. We can just see that it's diagonal in these B operators, right? So U, D, U daga, A. I just replace A with its eigenvalue decomposition, U, D, U daga. And now we just see that we just define conveniently this to be B, and this will be B daga. So this is B daga D B. Okay? And let's expand it in components. So there are n modes still, single particle energies, and BK daga BK. Okay? And so now we would like to understand the ground state of this Hamiltonian, which is already diagonal. That's standard. I hope, well, are there questions about this? And a way to understand the properties of the ground state of this Hamiltonian, I find it useful to actually do a Jordan-Wigner transformation into Pauli matrices, because that's where we have better intuition. So through a Jordan-Wigner transformation, we can rewrite this sum over K, EK, in terms of Pauli matrices. Okay, this is a particle number for mode K, so it looks like that in terms of a Pauli matrix, and this is nothing but EK. It's a simple n-qubit Hamiltonian where on its qubit we have just an operator like this acting, And so what we want to understand is the ground state of this. So these are now n qubits. And of course, you know what the ground state of this looks like. So ground state. The ground state of this will be some psi, some state, which is going to be a product state. On each spin, on each qubit, we decide whether we want up or down, 0 or 1. Okay? And we'll decide this depending on the sign of the energy. We want to minimize the expectation value of the Hamiltonian. So that's going to be a string of zeros and ones, where each x here would be either 0 or 1. It's going to be 0 if the energy is positive. If the energy is positive, we don't want to have that qubit in state 1. So, okay, and if the energy is negative, then we really want to have that energy. So as simple as this, that's the ground state. Okay, and now we just want to translate what this simple ground state implies for our correlation metrics. Okay, is it clear that this is the ground state? Okay, so let's do this. You know, sometimes it's good to make simple things simple before it gets out of hand. So let me consider an example. So suppose that the ground state looks like 0, 1, 1, 0, 1. That's because of the signs of these single particle energies. And so if we ask how much is, now going back to the fermionic operators, we can ask how much is the energy, or sorry, the occupation number of B3 dagger B3. And we just go here, and we see that on the third position we have a 1, right? So it's going to be 1. More generally, on this ground state, if we ask what's the occupation of particle K, or fermionic mode K, it's going to give us xk. Okay, that's by construction. But also we see that if we ask how much it is, how much. So let's do this. Yeah. But following with this example, if we ask how much we have, what's the expectation value of B, say 1 dagger B2, okay, what we see is that B2 is going to destroy this particle. B1 is going to create one here. The overlap is going to be 0. Right? This overlap is only non-zero if whatever we destroy, we create it again. Okay? So that means that expectation value bk dagger bk prime is going to be the following. It's going to be delta k prime. Okay? We really need whatever we do on this side. First, we need to undo it, or the overlap is going to be 0. So that accounts for this delta, and then followed by xk. Okay, so that's the characterization of all the correlations in this ground state. But of course, in these modes B, and now we need to go back to real space, to the ones that correspond to the modes A. But let me write this in terms of our correlation metrics. So what we are saying here is we have bk dagger bk prime is equal to delta k prime, and then what was this x? It was 0 if epsilon k is positive, and 1 if the energy was negative. Yeah, I've been introducing epsilons, there is. And now I would like to rewrite this in terms of the correlation, what I'm calling here the correlation matrix, mk k prime. And now we'll see why it is convenient to use this instead, which by definition is delta k prime minus 2 times bk dagger bk. Okay? So we already understand the ground state. And now we're just rewriting this correlation matrix. And you can convince yourself that that's delta k, k prime. And now the 0 or 1 transforms into a sign, into the sign of epsilon. So sign of E, the single particle energy of k. Okay? That's exactly why we choose this combination, so that this correlation matrix now is not 0 or 1, but plus 1 or minus 1. Okay? Just it's more convenient. And why? How can we see that this is convenient? It will become clear in a second. So let's go back to mn, which was defined as delta mn minus 2 a m dagger m an. Okay? And then what we see is how do we go from one to the other? We have to do the unitary transformation on the modes. This is in terms of A's, this is in terms of B's, right? So what we're saying is that M is equal to U, I'm gonna do this right here. So M is equal to U M tilde U dagger, right? I'm just undoing the change of variables from, so this is in terms of annihilation operators A, this was in terms of annihilation operators B. Okay, so I undo the change of variables. And so we have that the correlation matrix that we want is obtained from the simple one that we just computed, which had this expression, just by taking U and U dagger, going back to the original variables. Okay? And so this is, simple derivation, but the key result is this. The conclusion is that if A, remember, A is characterizing the Hamiltonian up there. If A is diagonalized by U, and it has the form U, D, U dagger, then our matrix M, right, if this characterizes the Hamiltonian, then the ground state, the correlation matrix for the ground state, is nothing but U dagger of what? Of M tilde. But M tilde, after all, what is M tilde? Well, this is just the sign of E1, E2, En, okay? Which is nothing but the sign of the diagonal matrix D, okay? The sign of a matrix, you can define it as the sign of a matrix with where you only keep the signs of each element. And so what we find is that here we just need to put the sign of D. And this is all that we need to remember in the end. That the correlation matrix for the ground state, okay, is obtained in a very simple way. You take the matrix, n times n matrix that represents the Hamiltonian, you diagonalize it. You take the diagonal part, and you just replace it. So D was E1, E2, En, and you replace it with sign of D, which is nothing but the sign of E1, sign of E2, sign of En, okay? And you undo the transformation, so U dagger. You conjugate by U. Okay, so that accounts for part one. How do we determine the correlation matrix for the ground state? Is that part clear? Other questions? Very good. So,
question?
Yeah.
What do we do for zero energies?
Sorry?
What do we do for zero single particle energies? How do we decide the sign?
If we have a Hamiltonian where there is a single particle energy that is zero, then the ground state is not unique, right? Because so we'll have degeneracy there, and actually, the question is not well posed. What's the ground state? Say if we want to study the entanglement of the ground state, but the ground state is not well defined, then we have not clarified what we want to study, right? So then you need to further specify what you mean, which state you want. That's not the problem. It's just that you didn't specify the problem enough. And one of the things we'll do is try to avoid that we have a zero single particle energy so that we know what the ground state is. Very good. Okay, so reduced density metrics. Actually, that part is very easy, and I just don't know what I should be using here. Maybe this one. That should do. And so, okay, so 2. How do we compute the reduced density metrics? And that really is a piece of cake. So what we're saying is that imagine we have a one-dimensional system or larger, and we have sites 1, 2, 3, 4, 5, and we want the reduced density metrics for the first 3 sites. Okay, so let's call this region A. Then what that means is we would like to understand expectation values of operator. So what is rho for part A? Rho for part A is whatever object we need to be able to compute any expectation value of operators that are only supported on part A. Okay, so it turns out then that all we care about are expectation values of operators. These are examples. Okay, this is an example of an operator which are supported only on part A. So what that means is M and N should only be in, we are interested in elements of this form contained in part A, right? So we restrict the values of indices M and N. Before they used to go all the way to the system size N, now capital N. Now we just take the values here, M and N, within the region that we care. Okay? And it turns out that then you can actually see that indeed, with that, if Wick theorem applies to the whole ground state, and you are interested in an expectation value for a concrete region, then Wick's theorem is still valid because you're talking still about the ground state, just you are paying attention only to a region. So the result of this is that we had this matrix, okay, which was N times N. And if this size now is L, what we're going to do, so this is a Wick matrix, and we're going to restrict our attention to a submatrix corresponding precisely to the entries where both indices are within the region that we're interested in. Okay? What I'm saying is that the reduced density matrix for part A is represented, and this is 2L times 2L, represented by taking M by a new matrix, correlation matrix M A, which is nothing but M restricted to part A. Okay? We restrict M to part A, to region A. So we just take a submatrix. Okay? Very good. And finally, how do we compute the entropy? So we now have subregion A, and we want to compute the entropy. So what we're going to do is the following. We're going to take M restricted to A, which by construction is Hermitian. That follows from the fact that M without the restriction was defined somewhere here. You can see that this is diagonal. This matrix is diagonal with plus and minus ones. And then if you conjugate by UU dagger, you still get a Hermitian matrix. So if we now restrict to a submatrix, this submatrix is also Hermitian. Okay? And so what that means is that we can diagonalize this matrix, this L times L matrix, and the diagonal this time will contain some values. I'm going to call mu1 mu2, mu L. Okay? Very good. And then what this means, the fact that we can diagonalize it this way, means that there exist modes, new Fermionic modes, C, which we define as being what they need to be, such that the correlations expressed in these modes are diagonal. Okay? We choose, if we diagonalize the correlation matrix, we find modes which are uncorrelated with each other. Right? Once the correlation matrix is diagonal, it means that there are zeros everywhere, except in the diagonal. That's C1, C2, C1 dagger, C2 dagger, etc. It means that C1 doesn't talk to C2. That's what it means. Okay? So we have found a set of Fermionic modes in which such that when we express the state in those modes, there are no correlations between the modes. So, and this actually is equal to 1 minus n mu I over 2, if you just remember where this is coming from. This 1 minus mu over 2 is the inverse of taking 1 minus 2 times the correlation matrix. Very good. So what does this mean? Let's try to understand what this means. So suppose that L is equal to 1. If L is equal to 1, then we only have one mode. And what we have is C dagger C. Expectation value is equal to 1 minus mu over 2. And remembering that we have particle number preservation, this is 0. This is 0. And then we also have that this implies that C dagger is equal to 1 plus mu half. That follows from the anti-commutation relations of C. And if you try to think about if you had one Fermionic mode and it has these expectation values, remember, it's one mode. So what we have is a density matrix, which is a 2 times 2 matrix, and we have already 4 expectation values, so we have completely specified. And if you put it together, this looks like this. Okay? So if we just had one Fermionic mode, and it fulfills this property, then the rest follows by particle number preservation and by anti-commuting character of C, then we have that this is the density matrix. And in this case, the entropy of rho is pretty clear. It's minus 1 plus mu divided by 2 log 2, 1 plus mu divided by 2, minus 1 minus mu divided by 2 log 2, 1 minus mu divided by 2. Okay? So if we had just one mode, we would be able to compute the entropy. It would be just the diagonal entry that we would get after diagonalizing the matrix. So what about if we have more modes?
Yeah. Can you elaborate a little more how you get the sensory matrix from the expectation value?
Mm-hmm. So if you have a Fermionic mode, maybe the fastest way is to do a Jordan-Wigner transformation. You realize that C dagger C is equal to 1 minus 2 sigma Z. Okay. But you also have that C is, what is it? I never remember. Sigma X plus or minus I sigma Y. Right? And so you can rewrite these expectation values in terms of expectation values for the Pauling matrices, which you might be more familiar with. And if you know the expectation values of the identity and the 3 Pauling matrices, you know rho. That would be a way to do this. Okay, it's simple linear algebra. Okay, so So what happens if we have that there is more than one mode? Well, in this case, what we've seen is that we have the C modes, right? We have L modes that we call C that are uncorrelated. And so at least it should be intuitive if this is not the proof, but OK. So one can see that, OK? And I'm happy to discuss this, but not now, that what we have is that our density matrix factorizes as a tensor product of the density matrices for each mode. This makes sense, right? The modes are uncorrelated. So the density matrix factorizes in this way, where rho I, each rho I, is of that form with a corresponding value. Okay. Very good. So if we had an expression like this, then the entropy for the density matrix, okay, the entropy for the density matrix, well, there is a property of the entropies that we didn't discuss, which is that the entropy of a product of two probability distributions is the sum of entropies. Okay? It's additivity of the entropy. And similarly, the entropy of a product of density matrices is the sum of entropies for each density matrix. So sum over I from 1 to L of the entropy of rho I. But we know what the entropy of rho I or of rho I is. I'm going to call that no, this one. Let me call this f of mu. Okay. And so what we have here is sum from I from 1 to L of f of mu I. Okay? So the summary is that we know, given a Hamiltonian, we know how to compute the reduced density the correlation matrix for the ground state. From this correlation matrix, we just select some submetrics corresponding to the region we're interested in. We take this submetrics, we diagonalize it, we pick up the eigenvalues, okay? And for each eigenvalue, we get a contribution to the entropy. And that's it, okay? So this had to be a bit rushed. And if you think that was rushed, you will be amazed how much more rushed is what comes next, which is we are going to do the other Majorana operators in 1 minute. But it's very similar. So hopefully we'll learn something. So remember, in general, we have a Hamiltonian. This is 2 to the n times 2 to the n. And we want to find a ground state. And that's a vector, which is 2 to the n components. And a reduced density matrix on some region of size L. And this is going to be a matrix 2 to the L times 2 to the L. And we should, in principle, be computing all the eigenvalues of this matrix. And that would take 2 to the L. We would have 2 to the L of those. And then we would just compute this by, it's a sum from alpha 1 to 2 to the L of these eigenvalues log 2 the alpha. Okay? That's what we would do in general. That's what you did yesterday in the tutorial. But today what we saw is that if the Hamiltonian is of this form with fermionic operators, then this is just an n times n matrix. And then the correlation matrix that we understood how to compute, I explained it there, that's just n times n. And we can limit, by just taking as a matrix, we get the correlation matrix for the reduced density matrix. Okay? We explained that by diagonalizing this, we get some L different eigenvalues mu, and we compute the entropy as the sum of contributions to the entropy. So if our Hamiltonian instead was written in terms of was quadratic in Majorana modes, okay? So which we saw last week. then it's a very similar story. Now we have a metric which is 2n times 2n. Okay. We can diagonalize the ground state by similar arguments as the ones we had here. We'll have a very similar expression, which you'll find in the tutorial. And so that's going to be a 2L times 2L matrix. We can, 2n times 2n. And if we're interested in just a subregion, we take this matrix and we just restrict our attention to a submatrix, which is going to be 2L times 2L. Okay? And we'll diagonalize that matrix, and we'll find that there are mu1, mu2, mu_n, and then also minus mu1, minus mu2, minus mu_n. This will be the different eigenvalues that we have. And we'll just take the positive ones and compute the entropy. Okay? Very good. So let's go. Let's spend 10 minutes with the notebook. Can I have the projector, please? So I'm opening the notebook that I've sent you this morning. And what we're going to do is we're just going to focus on the expressions the final expressions that we had today. And so I'll start by making sure that pyplot is on. And so let's consider this particle, fermionic particle number preserving Hamiltonian, which is quadratic, which is equivalent to the XX model. All I have here. So our goal now is to simply see how to exploit this formalism to compute entropies in the ground state of, say, a quadratic Hamiltonian in fermionic operators. And the first thing we do is we build matrix A, and this is something you already did. This is taken from last week. Okay, so we knew how to build matrix A. And in this case, you recognize this as we had nearest neighbor hopping terms, okay, with periodic boundary conditions or anti-periodic, depending. Very good. So this is our particular matrix A that we start from. And what we want to do is we want to diagonalize A. And actually, we can forget about the translation operator. It's not important for this. And so what you do is you fix n. Now, n, I'm going to fix the number of sides in this system to be odd. And that's precisely to prevent, we want to prevent a zero mode. Okay? Remember, if we had a single particle energy which was 0, then we don't know what the ground state is. The ground state is degenerate. So just to make sure that that doesn't happen, or you can ensure that that doesn't happen by choosing n to be odd. You can think about why. And then what we do is we just build this A for, say, 11. So we fix the size to 11. We build the matrix A. We diagonalize it. Okay? And we diagonalize it, and now we want to see what's happening with the spectrum. So we're going to plot the spectrum. Just to make sure that there is no energy with values 0, no single particle energy with value 0, and that's what happens. Very good. So we're happy with that. And from there, yeah, we're going to be using, today we're going to be using the unitary transformation U that diagonalizes A. And here we have it. So this is, it took me like an hour to explain this expression, but we can use it. We say the correlation matrix M is nothing but conjugating by U and U dagger, what? So we take the single particle energies, it's a vector, right? we only keep the sign, so we go from all these values to ones and minus ones, a vector of ones and minus ones, and we turn it into a matrix. Diag M just forms a diagonal matrix with that, and then we conjugate it by U and U dagger. And supposedly this is already the matrix M that we want to diagonalize. This is the correlation matrix. This is the correlation matrix that describes the ground state. Okay? Very good. And now I just make sure that it's a Hermitian. That's not necessary, but sometimes numerical errors spoil such properties. Truncation errors, machine precision. Anyway, and what I do here is just for fun, I look at the first piece of both. This is the first piece that we had in the original matrix A. And this is what the equivalent piece looks like once we have taken away the values of V and replaced them only with the signs. Okay? And you see that the structure is very similar. So here we had minus signs of the diagonal, and we keep the minus signs where we had them. But then there were many zeros that now are populated. Okay. And so now, how do we compute the correlation matrix for the reduced density matrix? Well, that's very simple. We just decide that we want to study, say, L max times a region of L max spins. So we just go to the matrix M, and we define MA as a restriction, as a matrix for L max times L max. Very good. And this thing here, this L, is just, let me show you. Yeah. So this L, I'm just producing all the system sizes that we want to analyze. So we're going to analyze system size 1, 2, 3, 4, and 5. Right. Sorry, the system size is fixed, but what I'm saying, the size of the region is going to be 1, 2, 3. We're going to compute entropies for one side, 2 sides, 3 sides, 4 sides, and 5 sides. Okay? And very good, so entanglement entropy, how do we compute that? Well, there was this expression that says diagonalize the density, the correlation matrix on whatever region you are considering, and look at the eigenvalues, and from the eigenvalues build the entropies by adding single contributions, okay, for each eigenvalue, and that's what this function is doing. And so we can compute all these entropies. And now let's plot the result. And we see the result here. It's very simple. So I wanted to put a partition where region A has 0 size, just for completeness. So when we have one side, we have some entropy. When we have 2 sides, another entropy, and all the way to 5. We could just, to check that things make sense, we can come up here and say, okay, let me, instead of considering only regions, so regions A that are all the way to half the system size, now I can consider going to the whole system. So I have 11 spins or 11 sides, and now what I'm doing is I'm computing entropies for 1 side, for 2 sides, for 3 sides, all the way to 11. Okay? And this is nice because what we see is that indeed the entropy for, say, 11 sides, okay, is the same as the entropy for just 1 side. Okay? It's not, these two numbers are the same. So this is a symmetry that we expected, and we are checking that it's there. Very good. So that's how you would compute entropies for quadratic Hamiltonians which preserve particle number. And then we can also use the second, we can also study systems which are quadratic in Majorana operators. Okay? And it's a very similar formalism, but instead now we have, instead of n times n matrices, it's 2n times 2n. And we can create, this would be, for instance, for a Hamiltonian, which is equivalent to the Ising model that we saw last week. So we could create this matrix C. Okay? And then we can diagonalize it. And again, we don't need translation operators, so I'm going to remove this. We can diagonalize it for, again, 11 spins at criticality. And yeah, it's basically the same. So we can plot the single particle energies to make sure that there are no zero modes. Okay? And then we proceed. So this sample code, you can use it in the tutorial tomorrow. There is no mystery here. So we can create, this is the expression that we had. We can, this is analogous to what we saw before. We again have to take the sign of the single particle energies and do whatever transformation we had done to diagonalize matrix C. Okay, U tag. Very good. And finally, correlation metric G for density metrics. Yeah, we do the same as before. Now we create our correlation metrics on part A by restricting the correlation metrics for the whole system to the region we're interested in. Okay? And finally, we compute the entropy, entanglement entropy, in a very similar way as before by adding contributions, by diagonalizing these correlation metrics on the region that we're interested in. We diagonalize it, we take the eigenvalues, and we compute individual contributions to the entropy, and we get some nice plot. Okay? But of course, the point of this is that now we can go up here and say, well, yeah, okay, 11, that was nice, but you know, what do we try? 1,000? I don't know. Maybe it won't work. I didn't try this. Exciting, huh? Okay, so it's taking some time. Oh, that's silly. Yeah, no, okay. So it did it. Okay, we got 1,000. And now I want to make sure that instead of going to all this, I just compute the reduced end. Yeah, I want to restrict how many diagonalizations of reduced density metrics we have to do, because that could take time. Though it looks like it's done. Oh, is it done? Yeah. Okay, so let's plot the result. Oops. Yeah. So it has to plot many things. I guess that's the challenge. Okay, and there will be a plot in a minute. And okay, so then what we will do is that there will be a tutorial tomorrow where you will use this strategy to diagonalize, to compute the scaling of entanglement entropy in very large systems of free fermions. And same way that yesterday you started to see some properties of the entanglement entropy of ground states, namely that the ground states were not very entangled compared to random states. So in the tutorial tomorrow, you'll be able to actually quantitatively study that. You'll see some logarithmic scaling appearing. And we'll be able to extract the central charge from it, which is something we couldn't do last week. And yeah, you know, I risked it. I thought it would be fun to see this. And it's still computing. So why is that?
Because n is too large.
Because n is too large. Yeah. Is that the exponential growth, or what is it? Why is n too large? No, n. So in the end, we are just taking a matrix which is 200 by 200 now, and we are diagonalizing piece by piece. So I guess, yeah, it has to do something 100 times, and its thing takes, what, a few seconds, but yeah. Okay, so did you do it yourself? Did you start this with 100?
Well, yeah, and I received the plot, yeah.
And it finished?
Yeah.
Okay, then there's a problem with my computer, and I'll find out. All right, that's it. Are there questions? If there are no questions, tomorrow what we will do, so the two lectures of this week will be purely discussing a scaling of entanglement without using the computer. It will be more about understanding, drawing conclusions from all the work that we've done so far. We'll focus on understanding what's special about the entanglement in ground states and what this is useful for.